Hello and good evening, everyone. My name is Konstantin. I'm the presenter for this session, and the presentation I will hold today here, I actually gave it a month ago at a gathering, a smaller gathering, but I had the feeling that it addresses kind of the entire CAE industry. It talks a lot about the current problems people are just overlooking. And I would simply want to share this talk because I think there's a lot to gain from many people out there. Just that you have a feeling. Now the talk has the title Computer-Aided Engineering from the Present to the Future. And what I'm talking about is I'm not highlighting nice algorithms or something. This is something like currently people ask me a lot about how do I do this and that. And these are the casual presentations. But here I am talking about the big picture. I am talking about what are current problems which are preventing us from using AI technology for computer-aided engineering, and how can we address them in like the upcoming time. So let's step right into the presentation. Briefly, the company. LASSO is my company I'm working at. Is a small CAE services company. It's 32 years old. It's quite old. In the beginning, we had our own FE solver, but for most of the time, we're doing structural mechanics services. We're really good at high-end simulations, very complex problems, and we do many different stuffs. Despite our doing a lot of automotive, of course. What we are mostly known for is that we are distributor for Better CAE Systems software in Germany. Those guys are great. We worked for a long time now together, and it's really cool working with these guys, building high-end simulation software for the automotive industry. What we like the competences from us are especially that we know what are high-end simulations, how do you model certain things, what are defects and problems. These are kind of like our strengths. But also we know since we are involved a lot with the Beta CAE system software, we know the high-end CAE processes. And as a new branch, which I'm working on, is a machine learning. So we are also now providing CAE machine learning services. And in this branch, I encounter many problems which I want to talk about in this talk today. So here's the table of contents. First, the motivation. Why do we do that? Machine learning at all. Then, why was there no machine learning yet? Everyone is using it. Everyone. And then I will get into what are the challenges preventing us from using machine learning on a broad scale. Now, what's the motivation to actually use machine learning? Now, the motivation is quite clear. In the end, it's always indirectly money. Some are more driven by money than others. But of course, we have a lot of manual work, and manual work is the most expensive one. And since the beginning of CAE, we had to do a lot of manual meshing. In the beginning, the tools were not really that automated and everything. So, yes, we want to kind of, or what we are always doing is to reduce this manual work and actually automate it so we are much faster and cost. Yeah, like we also, it's not a matter of money, but also I as an engineer, I don't want to be bothered with meshing, because meshing, it feels rather unphysical. It's not like a physical engineering problem. I want to build a car or something. Or make it better. I don't want to be bothered with dragging that part into the right position and wasting 20 minutes of time for doing that. Of course, people haven't been dumb. So they came up with automation techniques. And yeah, like for example, Ansa and Meta from the Beta suite, they have powerful scripting. They provide Python, for example, which is very, very good. And what scripting literally does nowadays is instead of you clicking the button in the post-processor or preprocessor, doesn't matter. You got a script pressing the button for you. So it does kind of the same as the robot you see here currently on the screen. The script is simply pressing the buttons for you. Now the problem is the tasks which we want to automate, they're getting more advanced. And when you get, for example, at a level like this robot here playing table tennis, which is a very complex human task to automate. It's by the way, a very nice machine learning reinforcement learning task. You can't do that with bare metal logic. This is very difficult to script analytically. So that's where machine learning gets into the process, which gives you the capabilities to automate many very complex tasks. But it's not so simple also to apply machine learning to CAE problems, as we will see in a second. So the main question is, why haven't we been using CAE yet? I mean, automation is really pressing hard. You can run simulations so easily. Like, departments get flooded with simulation data. You can easily generate 100 simulations if you want to. And what's even worse, you get more models, more use cases you have to test for, and everything. Like, it's seriously pressing. So automation, the need is there. The entire industry is indirectly crying for it. But why didn't we do that yet? Why didn't we apply these automation techniques? Now, let me kind of explain it with a little example. Some people come around these corners and they ask me, hey, Konstantin, I want to analyze these simulation files with the neural networks. How do I do that? That's kind of like the basic scheme people have in their mind. And then usually I'm like, slow down. You don't want to necessarily, like, what do you want to do? Because people, they think in methods, but you need to think in goals. What is pressing me? What do I want to automate? And when you find out what you want to automate, you can go into a machine learning, which is kind of more like a toolkit. And you need to find out, how do I achieve my goal? It doesn't necessarily mean that you want neural networks. This is something where I can break kind of the people a little bit apart to tell them, don't think, be so rigidly minded. But this is like the best level I can often get them. And there is something bigger around that. Like if you do that, you will still struggle. People will still, yeah, they might get good results or whatever. But it's not easy. And why is it not easy? Many people don't understand it. And the reason is because there is an even bigger picture. What you really want to do is not necessarily machine learning. What we are doing is data science. And the problem might not be related necessarily directly to machine learning, why we can't use these techniques. It might be related because everything around machine learning is still pressing. So why didn't we do this yet? Because in my opinion, CAE is by far not a data science. We are as distant as the moon away from that. We are slowly moving into that direction, sure. But we are very far from being a real data science. You will know in a second, like if you stop here the talk and you go away, whatever, take this site here from me. This is the most important message of the whole talk. The rest of the talk will be why. Why CAE is not a true data science, but very important, please take it in here if you want to quit. CAE is not a data science, a real data science, and that's the true problem we have. So this has been the thing. This talk has been in my mind for a long time, and also this graph. And data science, it's something much bigger. You can see, for example, here's machine learning. Machine learning is not in the beginning, and it is also not in the end. In the beginning is data acquisition and storage retrieval, which you need to handle in an efficient way in order to do machine learning on a reasonable scale. But also when you do machine learning, you are not done. You need to worry about visualizations to kind of translate the results, but also communicate them to your coworkers in a way that they can understand machine learning, or at least don't require to understand the algorithms in order to understand the results. And finally, no, this is something everyone forgets currently still, deployment challenges, like making things reliable. I will get into that also in a second. So we will just now walk this wheel along step by step and talk about every topic and the problems we have in our CAE community. Now the first problem, of course, is data acquisition. Now a manager would come along and say, hey, we can just do some HPC cloud service legacy data shenanigans whatever, take the data from there and yeah, train some magical model and that's it. That's kind of a very naive way of seeing the whole thing. But it's not so simple. For example, for us in instructional mechanics, we have a lot of non-standard data formats. Indeed, I can load an image in Python in one line of code, but then take your FE formats or whatever and try to get your hands on the data. It's very difficult, and often there are not really a lot of good interfaces which also provide you with a good performance. Now it's getting even worse. Let's say there's even like commercial formats or proprietary formats where you don't have an interface at all, a proper interface. And the only way by accessing the data in those files is going into their environments. Sometimes it's a post-processor or whatever. The issue is just these environments are then very rigid and you need to fit all you have in that environment, but you really don't want to do that. You just want this data. I don't need a post-processor if I just want to have the data. So the problem is now you might do it in their environments like algorithms and whatever, but then you're slow because a post-processor or preprocessor are not meant for machine learning. Those tools were never meant to automate such huge complex tasks and they don't provide you with the efficient means to do that. Now let's say you get your hands on the data. You get the data out of the file. Then you still have the problems. For example, in structural mechanics, the data itself is also not very simple. You have, for example, in structural mechanics, shells and solids mixed. And everyone who's a little bit in the theory, shells have dimensional defects. You have kind of like something 2D and 3D mixed, which is inconsistent. This is highly pressing. Like you need to reformat the matrices. You need to be reasonable how you care for integration layers and everything. So you need to make up your mind how kind of the data is treated in a consistent way. Also, never forget you not only have meshes, which are very irregular data structures. You have time series. You have text data, log files. You can also use them. There's a lot of very, very different data types. And all of them are partially hidden in very cryptic ways and not very good parsable. From the input formats to the output formats, it's always the same story currently, very sadly. Never forget you also get dirty data. So sometimes you get unphysical effects or rounding errors or something like that. And then you have unphysical values. And yeah, it's very like, if you do high-end, not high-end, but also a very explicit crash simulation or something, a lot of dirty stuff is happening in there. But this is not the whole story. Please be aware, I want to bust some myths here. Simulation data is not really cheap to acquire, even if you use an HPC or a cloud service. I mean, if you have an HPC and it's not at 100%, go ahead, use that. But the problem is, for example, we watch cloud services and a car crash costs around $4 to $20. This is not really cheap because you might run a few hundred simulations, find out that you had a bug and need to rerun them. And you will end up with quite a lot of money. So please be careful when you say simulation data is not cheap, especially when the runtime is still quite long for complex models. Please be aware of that. Also, databases are not cheap to kind of store all the data and everything. So it's not so simple to get their hands efficiently on the data. But let's say we can do that. Now we need to store our data somewhere. What we're currently doing is we store it on files and disks. So the files, or sometimes this files in the database, it doesn't matter too much. Files are files. And it's quite simple. We have been going with that road for a very long time now. Outside of CAE, people might be laughing a lot because they're used to also more complex ways of more efficient storage. If you store it in a file, for example, it's kind of your job, like you need to extract the data yourself out of the file. That's a little bit of a problem because we can't use a post-processor as stated previously. But this makes it usually quite slow, especially because data formats, what do you want to have when you have a file? You don't necessarily want to read like 100 MB file entirely into memory, it's slow. You only want to read kind of like maybe a result field or something, like a chunk. But you cannot read a chunk if you don't know where it is. And some FE formats are screwed up so much that you need to go the whole file through until you find the chunk and then load it. And this is a little bit the devil in those data formats. They're quite inefficient to deal with. So file is really slow. Of course, you can, if you have a bigger company, you can use a simulation data management solution. And oh my gosh, if you are a bigger company and you really can see some usage in that, do it. Go ahead. It has a great utility. You get versioning for simulation files. I saw in production so many issues which would be prevented if people had simulation versioning. It's so great. It's the same like in the coding industry. We would never go without Git anymore. it's hard. Important here is you need to have a data API, otherwise you don't get the Git data out. For a company like us though, we are a rather smaller company which have very diverse tasks. So it doesn't make sense for us to use for everything an SDM solution, because it's complex and often, like I said, simply overkill if you just have one guy or one woman working on it. So it doesn't really make that much sense in every case. Now you still have a third option not everyone is thinking about. Why don't we just take a database which is out there? The Apache Foundation, for example, has very good databases. They got a great performance, I can promise you that. You can run some of them on your laptop, or you can run them on a huge cluster. They are really awesome and scale well. They come with a lot of utilities. It's so awesome what people built there. And also, if you start with them and you don't make them too big in the beginning, they are not that expensive. Never forget, inserting the data into the database is still your job. But if you can live with that, then you will have a good performance. When the database grow though, be careful. They become quick, very big. And when they become big, they become very quickly also expensive. At bigger companies which have databases, you need to have at least one person, 1 to 3 persons, let's say that, with vacation and everything, which take care of the database, which tune the network and everything. So when it becomes big, it also gets expensive. Be aware of that. But from that point of view, it's not that bad of a choice. Now, let's say we have storage done. We can retrieve our data from file. Sometimes file is also fine, by the way. It's not the best way, but it's fine. Then we get into machine learning. Now, machine learning is a huge toolkit. You get a lot of algorithms in there. And I try to divide it here into the main categories which are nowadays used. Now, you got unsupervised learning, which is kind of like, let's see what we find in the data. So you don't know what's ahead. There is semi-supervised learning, which is, I know for a certain fraction of the data what it is, but I want to find out what the rest is, which is kind of like, you can use it for recommendation systems to recommend a movie and find out who else liked or disliked the movie. Then you get supervised learning. Supervised learning is like a very traditional optimization where you have something like an airfoil and it's optimized for drag, and drag is kind of like the target. And this is like supervised learning because you have a target value you can train for. And then you have reinforcement learning, which tries to automate human tasks in the context. So you take a task which is maybe a little bit more complex and fuzzy, like I showed before, and you want to let a machine do the automation. If you start here, don't get into these topics. Please remember the neural network example from the beginning. You want to first ask yourself, what do I want to do? Or at least, what costs me a lot of time? So what's worth addressing? This is the most important step. Don't just run into the scissor. Now here coming a few warnings. I'm the warning guy here because there's a lot of hype for AI currently. And I'm I'm not very happy about hypes, because the methods get overhyped too much, and then people at some point will find out like there's discrepancy between reality and hype, and yeah, it causes more trouble in the end than the benefit. So I just want to warn you here. And this is a site I got from Peter Battaglia from the Google Brain, and it was in a paper I read this June. And it states there is no default deep learning component which operates on arbitrary relational structure, which simply says you cannot just take data and plunge it into a network. This will not work. You will need to make up your mind how to build like an AI regarding that. Indeed, AI, building machine learning algorithms and chains is very out of the box. It's like hacking. You need to try a lot, understand what the machine does with data, how the data is working, what makes sense in terms of the data, what features to use, and so forth. So it's not just drag and drop. And you can kind of generalize this quite well, this statement, in my opinion. Then there's also a second hint I want to give at this point. People, they're just like, yeah, let's throw a neural network at it, woo, and everything will work fine. No, not at all. This statement from Grover, it kind of states, consequently, any model that jointly aims to predict the set of weather variables should leverage knowledge of the tight statistical couplings that are based in physics. It simply states that don't learn simply anything. If there are so tight couplings, it might be worth computing a few things instead of learning them. This saves you samples and makes it much more efficient. So don't just stumble ahead and go with the machine learning rocket launcher to shoot everything. No. Make up your mind and think about what you really need. Now this was a nice example to explain a little bit unsupervised learning to you. It is an example from my PhD, and it's quite simple. This is a rail, which is something like a crash-absorbing structure in a car, and it's getting crushed by a small plate, which is like a barrier the car drives against. And what you can see is that it's sometimes buckling in the top and sometimes buckling in the rear. I did here 1,000 simulations. Be aware, I don't need 1,000. You can also do this with 20 or something. It doesn't matter that much. And I did the variations with the design of experiments study. So I had 173 design variables, which minorly were different. Also, these models had different meshes. Please be aware of that. And the idea was kind of like, I ran 1,000 simulations, but I couldn't compare them anymore. I mean, this is something we have very commonly currently in the industry. Just think about. I mean, here I was sitting in front of my computer and was like, I will never be able to go through 1,000 simulations and compare these rails. Okay? This is too much for a human. And if you think about bigger computations like a car, I saw many people, they knew, there was a problem in the front of the car. They looked all the time at the front, fixed that problem, and never saw that at the rear another problem appeared or overlooked it. So it's very like when you have big simulation models, you don't need to have 1,000 to be in trouble. 3 or 4 is already enough. Because you will not have the time every day to watch it in very high depth. And this is where machine learning comes in, where you say, come on, we don't want to have to rely on the algorithm, but we want to have an algorithm pointing a finger so I know that I can simply check certain things with relevance. Now, these are frequent challenges you have. Like, if people show you nice algorithms these days, ask them for those questions. Those are really nailing the difficulty levels. You have to have different meshes. So I mean, that's not too difficult to cope with different meshes, but it's a computational effort you still have to take. But it's getting worse when you have different versions. For example, you have a hole, you have ribs, additional removed ribs. The algorithm I'm showing you can cope with both of these without a problem, really. Where most are still struggling is when you start morphing. I don't have it here, but morphing the part, stretching it and everything, strong local morphing. And never forget that machine learning is not reliable. You might have, for example, the blue dots is the data, and you might have to fit a model through it. Here it is overfitted, and there might be, because some parameter settings or simply, yeah, you took it wrong, a local defect where you make a really bad prediction, which is not very close to data. And this is not user-friendly to have it, because if you simply build a machine learning model, deploy it, how does the user know that it's reliable whenever he asks the model? So be aware that there are many bad things in the background you need to take care before you give something like that an engineer. Indeed, I even believe that it makes more sense to simply help the engineer understand the model better, but let him take, for the moment, most of the decisions, because a machine learning engine is very flawed. Also sample counts. We don't have too many samples, so you need to tune for less samples, which is really bad for neural networks because they really excel at the reason why it became so famous and something is because neural networks work very good with very large databases. Then neural networks really accelerate and can use that. Many algorithms cannot do that. Okay, just like the last warning when you see these challenges I just posted is CAE machine learning is currently like a battlefield. On a good day, you might not lose anything. But believe me, on some days you hit two mines with both feet. You will skyrocket into the heaven. I can promise you. Sometimes you encounter a little problem, which you think is nothing, and you will find out that you will need a big cluster to solve that very fast, or you will find out that it's some theoretical gap. So it's very, very difficult to do it in a very consistent way for many different models and so forth. This is like the real world is very challenging here. But I kind of stretch it too far. Let's get back to the rares. So I compared 1,000 of them. I wrote an algorithm to compare them. And now I want to visualize and show you what the result was. I might fail at this point just as a little warning. But that is fine. I calculated it in. Please stick with me. And you will get an enlightenment in one slide or 2 slides. So what I did was I built this visualization. This was one of the first results I got during my PhD. And they're called low-dimensional embeddings. And we built them for words, for images and faces, cat faces. Every machine learning presentation has to have cat faces mentioned. And of course, you can build them also words, I hope I recognized. And how does it actually work? It works such that every dot here is one of the simulation results. So those are 1,000 at once. And the closer those simulation dots are, the closer their results have been. These axes are kind of like statistical principal axes. They are difficult to interpret. So they themselves are not that important. What's important is the relation of the dots in this plot. This is the most important. We see 2 clusters and 2 dots. Now, it's hard to explain to you how this actually works here. And I might even have failed to explain it in a proper way to you. Because visualization is a key effort you really need to leverage. Visualization, sometimes an image, or very often an image, is not enough in machine learning. Machine learning is so difficult to understand, for example, neural networks, that interactive visualizations and tapping into the structures in an interactive way is mostly very important. So that is the reason why I will approach this now with a proper way. So here we have again the same plot we had just currently, 1,000 simulations of the rail. And in order to understand it, you can simply hover here along the dots and you see the simulation results. And you can see that those simulation results, they don't differ a lot here. Like I'm hovering the buckle roughly around the same corner. But then you see the second cluster. And when you hover just above them, you see, those are all which were buckling in the bottom area. So in one glance, we see the entire behavior I had seen in just 2 samples previously also. I tricked that, of course. But you can find even things you didn't expect. For example, you see the green one is very long. So when you sweep along, you see that buckling didn't occur necessarily only in the top. It was also at around here 40%. And that's why it's called unsupervised learning, because you might encounter something you were not looking for. This is the great side of this. Unsupervised learning is also usually more difficult. What I really liked also was you have outliers. You can see them directly which one was not in default behavior. This one buckled just much lower. And just as a note, this was just more rare. I did another investigation to research this. And this one here, for example, it's between the clusters and is simply buckling at top and bottom at the same time. I even had found solver bugs and everything in clouds like these. So these are really awesome to investigate the simulation behavior. Also note that there is a much finer grained structure. For example, when you go here down, you don't have any initial buckling here, but when you go to the other side of this bandwidth, you have slight buckling here. So if you dive deeper into these clusters and everything, you can find also different behavior and finer grained differences. So these are low dimensional embeddings. And just imagine, you just, with me together, in 1 minute, investigated 1,000 runs. So fast. This is really like the leverage of machine learning. So let's go ahead. The question now is, of course, how to avoid buckling bottom. Or it's not very obvious because I didn't mention it yet. But we don't want to have this buckling behavior here. We want to kind of have the car buckle at the location where the impactor is hitting from up. But we don't want to have it buckling in the bottom where the passenger is right sitting underneath. So we want to have stable folding from the beginning where the impact is down to the passenger's cell. So we want to avoid this buckling bottom. And we investigated with supervised learning. Supervised learning, in that sense, we used decision tree learning because it tells you how it thinks, and you can understand what might have caused this buckling bottom. Neural networks will not tell you how they think. It's possible, but you have to dive deep. So here at this point, what you see is a tree, and it's giving the decisions it took to predict whether buckling bottom occurred or not. Now, what I as a machine learning scientist can do, I can sweep through this tree and manually find the right decisions and everything. But I know this is nothing for you because communication is still an issue. I cannot give a decision tree to a CAE engineer who's sitting in a department and working on seriously real-world problems. I need to do something to wrap it up. So we wrote kind of a wrapper, which was a chatbot. And what you could do is you could ask the AI for design recommendations. So you could ask, for example, how do I prevent the buckling bottom cluster, and you got a recommendation or multiple even. Here, buckling bottom occurred around 0 degree. There's a mistake here. There must be a minus sign. And when you kind of hit straight with the impactor onto the rail, then it was also sometimes buckling in the lower area. And you can avoid this in the design by simply inclining the top part a little bit in the design. Also, we found other ways to use even stuff we already had in our database, for example, the intrusion of the car. And you could even ask for design recommendations. Sometimes they have very unuseful. She was telling like, yeah, you want to have less intrusion, drive slower. And then I'm like, yeah, appreciate it. But of course, there are also alternatives, like if you cannot drive slower, of course, reinforce these sheets. In this case, the motor mount was a little bit too weak, so the motor pressed into the car and caused a high intrusion. So everything is fine, isn't it? Like, we build nice visualizations, we build nice jet engines, whatever, which we are also still advancing. are, so we're done, or are we? And of course we are not, because you forgot one last point: deploy. This is no one is thinking about currently in CAE. Everyone is writing his scripts in preprocessor, postprocessor, outside, doesn't matter. Everyone is writing his little scripts and handing it over to everyone, and it's often very failing and everything. Why? Because deployment has a lot of challenges, and people are not addressing these challenges in a very proper software data science way. So what you need to have is testing. You need to have a testing suite and have also at best continuous integration, which simply is like a testing automation, automatic testing of every commit you make to your code changes. This is really like, don't just take a script and hand it out. If you really want to make sure that it's used in production, you need to test it in a very good way. And also, if you need to have high reliability for a customer or something, and like they have an automation pipeline and really want this one component to automate something, you need to do failure mode analysis to be sure or understand the failure cascades and everything. So you hit the reliability which is demanded by the customer. So don't forget, deployment is not necessarily an easy task, and it's not simply shipping a script and that's fine. Now you might also understand what our company is doing. We're doing literally everything of that. We're providing, of course, consulting in a strategic way. Some people want to know how to engage and everything. We're doing trainings and so forth. Also in terms of algorithm, we analyze data sets like you can just give us and you get back nice reports, interactive reports and everything. But we also are willing and do build and deploy tailored solutions to customers desired on their use case. So that's another nice thing we do around here. It makes a lot of fun. Tailoring things is really a lot of fun. So if you have any further questions at this point, you can just mail me at konstantin.dietz@lasso.de or www.lasso.de also, which is our website. There you can find a contact for our company. I would be really happy if people out there would simply, if you have like ideas or questions or whatever, simply ask me. I'm really open for the voice of the community. Because it really values me a lot, what is bothering you in your everyday, and where do you also see potentials of machine learning. Also for the higher ups and managers, I also value those opinions, of course. I'm very open to talks with everyone, especially because you get different perspectives, and I'm very gladly to respond to those. So I hope you enjoyed my talk here. It's a little bit long, but I think it was worth it. And I wish everyone here a very nice day.